Okay, this is Math 131, section 3.5. We're talking about symbolic arguments in this section. And basically, we're determining whether a symbolic argument is valid or invalid. Okay, so a symbolic argument consists of a set of premises, okay, and a conclusion. Okay. And we call it a symbolic argument because we generally write it in symbolic form to determine whether it's valid. So that's what we'll be doing with these arguments, is seeing if they're valid using symbolic logic. Okay, so we say an argument is valid when its conclusion necessarily follows from a given set of premises. In other words, that the conclusion makes sense based on what we said had to happen first. Okay, premises would be what happened first. And then we can say an argument is invalid, or we call it a fallacy, when the conclusion does not necessarily follow from the given set of premises. Okay, so we have to see if the conclusion makes sense, that would happen if the premises happen. Okay, so we're going to start with talking about the law of detachment. Okay, and that also is called modus ponens, but don't worry about the Latin name. Okay, we write this argument this way. Our premise 1 is if P then Q, and our premise 2 is P. Okay, and their conclusion is, and you'll see these three dots, and that means therefore Q. Okay, so how we would write that is if. Now we have to put premise 1 and premise 2 in brackets. So if premise 1 and premise 2, so there's premise 1, okay, with parentheses, and premise 2, and then we have the brackets here to group those together, then conclusion. Okay, so we have to group all this stuff together as the if part. Premise 1 and premise 2. Now think of like our thing with the passing exam 2 and passing the class. So my premise 1 would be if you pass exam 2, then you pass the class. Okay. Well, premise 2 says you passed exam 2. Therefore, you must have passed the class because I said if you pass exam 2, then you have to pass the class. Do you see how this kind of makes sense logically? That this law of detachment, this is always a valid argument. Okay. So here's how we determine whether an argument is valid or not. Okay. First step is write the argument in symbolic form. Okay, so use symbolic logic. Then we compare the form of the argument with forms that are known to be either valid or invalid. Okay, in other words, that one we just looked at is always valid. Okay, if there are no known forms to compare it with, we go to step 3. Okay. So step 3 says if the argument contains two premises, write a conditional statement of this form. Look at premise 1, premise 2, and premise 2, conclusion. Okay, and then construct a truth table for the statement above. Now we should have this. Let me rewrite this. Hold on. Okay, so it should be saying if premise 1 and premise 2 in parentheses, then conclusion. Okay, so that's what this should say. If premise 1 and premise 2, then conclusion. And construct a truth table, the statement above. Using symbolic logic, we would have P1 and P2 in parentheses because it's this and this, if, then conclusion. Okay, so we'll be looking at this truth table for this statement in symbolic logic. If premise 1 and premise 2, then conclusion. Or in words, if premise 1 and premise 2 in parentheses, then conclusion. And if that's always true, then we have a valid argument. But it has to be true for every case. Okay, and then we say if the answer column of the truth table has all truths, the statement is a tautology, and the argument's valid. That means we have all truths, the argument's valid. If it does not have all truths, the argument is invalid. So all we need is one false to show that's not a valid argument. Okay, it has to be true in every case. Okay, so for our first example, using words, this will be our premise. If you have enough reward points, then you get a free flight. Okay. The second premise is you don't get a free flight. Okay. And then the conclusion is you do not have enough reward points. Okay. So let's think about that for a minute. It says if you have enough reward points, then you get a free flight. And then you didn't get the free flight. So it kind of makes sense that maybe you didn't get enough reward points, because if you did, you would have gotten the free flight, right? So we can say, you know, from reading this, it kind of seems logical that it's a valid argument that you must not have gotten enough reward points. Okay, let's look at it in terms of symbolic logic, though. Okay, so we'll let P be you have enough reward points, okay, and Q be you get a free flight. Remember, they shouldn't have nots in them, they should be affirmative statements. So the first premise is if P, then Q, okay. The second premise is negation Q, because we said you don't get a free flight. So those are our two premises, right? And then we're saying if this and this, so if this thing and this thing, then negation P. And our conclusion would be you don't have enough reward points. Okay, remember that was what we said that conclusion was. Okay, so we're looking at this. If premise 1, this is premise 1, P arrow Q, and premise 2, in brackets, okay, then negation P, okay. So let's look at the truth value of that. So here we're going to use true, true, false, false, and true, false, true, false. So here's P, if P, then Q, true, false, true, true. Remember, the only thing that gives us a false is true, false. Okay. Negation Q would be false, true, false, true. And we're looking at the and of these two. Remember, they both have to be true. So we have a TF gives us a false, FT gives us a false, TF gives us a false, and then TT gives us a true. So this is what we have for the and of the two premises. Okay. Now we're going to arrow that if, you know, take these two and, if those two ands, then negation P. Okay, so true, true, false, false, we just carry over here and change to the opposite. So this becomes false, false, true, true. And now we're taking if then of these two. Okay, so false, false gives us true. False, false gives us true. Remember, it's if then. False, true gives us true. Remember, if they start with an F, then it's always true. And then true, true gives us true. So we can see that this thing is a tautology. It's always true. Okay, so premise 1 and premise 2, bracket, arrow, conclusion. And then we find the truth value of that. And if it's always true, then we say our argument is valid. So this is indeed a valid argument, and we've shown that. Okay, let's look at some common standard forms of valid arguments. So this is standard forms of valid arguments. The law of detachment says if P then Q and P then Q. Okay, let's look at this in the context of our exam, problem. Okay, so if you pass exam 2, then you pass the class. Well, you passed exam 2, so therefore you must have passed the class. You must pass the class, right? Because I said that. Okay, so this kind of makes sense just on its observation. Okay, the next one is the law of contraposition. Okay, if P then Q and not Q happens, then therefore not P must have happened. Okay, let's apply that to the same example. So if you pass exam 2, then you'll pass the class. You didn't pass the class, so therefore you must not have passed exam 2. Does that make sense? Because in order to, if you didn't pass the class, then you must not have passed exam 2. Okay, that was the one we just looked at in the previous example. Okay, the next one is the law of syllogism. Okay, that says this: if P then Q, if Q then R, and if both of those happen, therefore then this will happen. If P then R. Okay. So think of it this way. I'll highlight these. So these are premises, and this is our conclusion. Okay. Let's add another thing to this. So let's say R is then you will graduate. Okay. So if you pass exam 2, then you will pass the class. If you pass the class, then you will graduate. The conclusion says if both of those are true, then if both of these are established as premises, that if P then Q and if Q then R, then we can also say if you pass exam 2, then you will graduate. Okay, because this implies that if you pass exam 2, you will pass the class, and then it says if you pass the class, then you will graduate. So it's kind of like dominoes. Like these are dominoes stacked up, and if this knocks this one over, then this one will knock this one over, which means this one will knock that one over. Okay. And the last one we'll look at here is called disjunctive syllogism. Okay. Don't worry about the terms. I'm not going to ask you to memorize these terms. Okay. So P or Q is our first premise, and then negation P, and therefore Q. Let's again apply that to our example using the class thing. You pass exam 2 or you pass the class. Okay, so one of those happened or both of those happened. Okay. But we're also saying that you didn't pass exam 2. So if one of these happened but the first one didn't, that means the second one did. Okay. So therefore Q. Does that make sense? So you either pass the class, pass exam 2, or you pass the class. But you didn't pass exam 2, so you must have passed the class. So that's disjunctive syllogism. Okay, here are some standard forms of invalid arguments. These are not always true. Okay. The first one is called fallacy of the converse. And that's we're saying if P then Q, and Q are our premises, therefore P. Okay. Let's apply that to our example using the exam thing. If you pass exam 2, then you'll pass the class. Okay. And the second premise is, well, you passed the class. That doesn't necessarily mean you passed exam 2. Remember, we could say, just because you passed the class doesn't mean it didn't say you had to. It's not an if and only if. So there could be a case where you didn't pass exam 2 and still pass the class. Okay. The only thing that would violate this again is where you passed exam 2 but you didn't pass the class. A true false. So we could still have these two happen, but we can't say necessarily that you passed exam 2. Because you could still pass the class without passing exam 2 with an if then. Okay. So that's fallacy of the converse. Okay. Fallacy of the inverse says this. If P then Q is our first premise, negation P is our second premise, and then therefore negation Q is our conclusion. This is not a valid argument either. If you pass exam 2, then you'll pass the class. Okay. You didn't pass exam 2. That doesn't mean you won't pass the class. Remember I said that just says if you pass exam 2, you pass the class. It doesn't say what happens if you don't. So we don't know what's going to happen here, okay, if you don't pass the exam 2. So we cannot conclude that you don't pass the class. So that's a fallacy of the inverse. So these are both invalid arguments. They're not always true. Okay, so let's identify our standard argument. So we'll see if this argument is valid. Okay, so the first thing says, if you are on Instagram, then you'd see my pictures. Okay. And then the next premise says, if you see my pictures, then you know I have a dog. Okay. The conclusion is, if you are on Instagram, then you know I have a dog. Okay. So this is actually one of the valid arguments we looked at. So let's translate the symbolic logic. So P is you are on Instagram, Q is you see my pictures, and R is you know I have a dog. Okay. So here are our premises: P arrow Q, if P then Q. Q arrow R, if Q then R, and then our conclusion is P arrow R, and we can see that this is the law of syllogism and it's valid. That's one of the things we looked at. Remember our domino thing? So it's kind of if A then B, if B then C, then if A then C. So if the first thing happens applies the second thing happens, and the second thing happens applies the third thing happens, then the first thing happening would apply the third thing happening. Okay? Let's identify a common fallacy. If it is snowing, then we put salt in the driveway. Okay? And the other premise is that we put salt in the driveway. Okay? Now that does not mean that it's snowing. Remember, this is an if-then. It's not an if and only if. So we say if it is snowing, then we put salt in the driveway. And then we do put salt in the driveway. Now maybe we just put salt in the driveway when it wasn't snowing. Maybe it was just ice or hail or something. Okay? So it doesn't necessarily mean that it's snowing. Okay? So let's put that in symbolic form. P is it is snowing. Q is we put salt in the driveway. Okay, and here's our first premise: if P, then Q. Okay. Our second premise is Q. Okay, and then our conclusion is P. Okay, so this is the fallacy of the converse. Okay, and so it's not a valid argument; it's invalid. Okay, and we can apply that to the two common fallacies that we looked at. And that fallacy of the converse was one of them. That was this one. Okay. Okay, let's see if this makes sense. Our first premise is, if it is snowing, then we put salt in the driveway. Okay. And our second premise, it is not snowing. Okay. Does that mean we do not put salt in the driveway? Not necessarily. Let's go back to our example. Okay. If you pass exam 2, then you will pass the class. Okay. You do not pass exam 2. Okay. Does that mean you don't pass the class? Not necessarily. I could still pass you if you don't pass exam 2. Remember, that's not an if and only if, that first premise. Okay. So this is another one that's a fallacy. Okay. So let's look at that symbolic logic. P, it is snowing. Q is we put salt in the driveway. So our first premise is if P then Q. Our second premise is negation P. And then our conclusion is negation Q. So this is a fallacy, the inverse, and so we say that's an invalid argument. And if you forget these, if you're not sure if this is or not, you can always look at the truth value. So we would look at if this and this, then this, and we'd say it has to always be true in every case. Okay, now let's get to truth tables and looking at valid arguments. Okay, so here's our first premise. If my cell phone company is Verizon, then I can call you free of charge. Okay. And the second premise is I can call you free of charge, or I can send you a text message. Not an if, but an or. Okay. And then the conclusion, there's 3 premises. Okay. The third premise is I can send you a text message, or my cell phone company is Verizon. Okay, so we have 3 premises. And then the conclusion is, well, my cell phone company is Verizon. That is kind of confusing. How do we figure this out? Symbolic logic. Okay, so let's translate. Okay, so here we have, let's make P is my cell phone company is Verizon. Q is I can call you free of charge. And R is I can send you a text message. Okay, so the first premise is if P then Q. If my cell phone company is Verizon, then I can call you free of charge. Okay. The second one is Q or R. I can call you free of charge, or I can send you a text message. The third premise is R or P, or I can send you a text message, or my cell phone company is Verizon. Okay, and then our conclusion was my cell phone company must be Verizon. So here's our 3 premises. Okay. 1, 2, 3, and then conclusion. So we're going to look at this and this and this. If those are all true, if this and this and this, then P is our truth table. So we're going to write, here's premise 1. Should be a bracket here. Okay. Premise 2, and premise 3, then conclusion. So let me just write that using kind of in general form. Okay, so we're saying if this, premise 1 and premise 2 and premise 3, then conclusion. So this is the symbolic logic way of looking at that. Okay, here's premise 1. Okay, here's premise 2. Here's premise 3. Make sure they're all in parentheses because this is one premise. This is one premise. This is one premise. So premise 1 and premise 2 and premise 3, bracket, then conclusion. So let's look at the truth table. Again, since we have 3 simple statements, we're going to start with 4 T's and 4 F's for P. And then 2 trues, 2 falses, and then 2 trues, 2 falses again for Q. And then remember, our circuit goes back and forth. TF, 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 TF. Okay, so our first premise is P arrow Q, and that would be true for TT. True. True false gives us false. True false gives us false. False true gives us true, false true gives us true, false false gives us true, and false false gives us true. So this is the truth value for P arrow Q. Okay. Second premise is Q or R, so we just need 1 true, so that's true. 1 true, true. 1 true, true. No trues, false. 2 trues, that's true. 1 true, 1 true. No trues, false. Okay, so there's our third premise. Okay, so that's step 2. Our second premise, sorry. Our third premise was going to be, don't worry about the step numbers down here. I'm going to do the premises first. Okay, so third premise is R or P. So we're looking at R and P and looking for 1 true. So we have 1 there, so that's true. Sorry, there. P and R, P or R, T, we have 1 true there, so that's true. We have 1 true, so that's true. We still have 1 true, so that's true. Okay. We have 1 there, so that's true. None there, so that's false. 1 there, so that's true. And then none there, so that's false. Okay, so I did this premise, and this premise. Now let's look at the and. Now you can do this 2 at a time, but you can also do 3 at a time too. So let's do it 2 at a time first. So we're going to do these for 2 first, and we're going to do ands. So we need true and true to get a true. True and true gives us true. False and true gives us false. Okay. False and false gives us false. True and true, true. True and true, true. True and true, true. True and false, false. Okay, so that's the first and. Now we'll do the second and. So we have to do it with this one. Okay, so we're going to take this thing because we just did these two. So this is all of these. So we'll take this thing and this thing. Okay, so we're going to compare this one with this one and put it here. Okay, so true and true gives us true. True and true gives us true. False and true gives us false. False and true gives us false. Remember, we need two truths. True and true gives us true. Okay. True and false gives us false. True and true gives us true. And then false and false gives us false. So now we've done all of these. This is the final and there. We're putting all those ands together. Okay. And then we're going to look at this thing, arrow P. So we're going to compare this to P. Okay. And we're looking at if then. So remember, true, true gives us true. True, true gives us true. False, true gives us true. False, true gives us true. True, false gives us a false. False, false gives us a true. Remember, we're doing arrow, right? True, false gives us false again. And then finally, false, false gives us true. Okay. So if we look at our truth value finally for this thing, this is our final, term where it's valid. We've got a couple falses in there, which means this is not a valid argument. It has to be always true. Okay. Now, what I was telling you before about this, if we do the three premises, okay, first, if we're doing this one and this one and this one, we can just look for three trues. Okay, in other words, to be true, all three of these premises have to be true. So true, true, true gives us true. True, true, true gives us true. False, true, true. Oh, wait a minute. Sorry. Let me start over with that. We're not looking at this one. We're looking at this side. So to determine whether this premise and this premise and this premise is true, and that would be this column. Sorry, that's this column. We're just looking to make sure that all three premises are true. So true, true, true gives us true. True, true, true gives us true. False, true, true gives us false because they have to all three be true. False, false, true gives us false. True, true, true gives us true. True, true, false gives us false. They have to all three be true. True, true, true gives us true. And then true, false, false gives us false. So that's just kind of a shortcut way of doing that, is that we don't have to do this and first. We can do them all together. Okay. And saying this and this and this means they all three have to be true in order for the final result to be true. Okay. And then we would do the arrow with a P. Okay. So again, this is not a valid argument because we don't have all trues in our final column. Okay, so the answer was column 7 is not true in every case, thus the argument is a fallacy or invalid because we need all trues for it to be a valid argument. Okay, we'll look at some examples of this in class and kind of, look at more, maybe some more detailed examples.